Hi, my name is Thomas Wise, and this is Lab 2 for Physics 2211, looking at gravity. So the purpose of this lab is to view an item falling and the effects of the forces of gravity and drag on said item. The fundamental principle that is used here is Newton's second law, which is F net is the sum of all the forces. In this case, we are looking at the sum of the force of gravity and the force of drag. Main result of this lab will be viewing the air that is caused from drag and how that affects the way we would expect an item to fall if there is noticeable amounts of drag on it. For the main setup here, I used a crumpled up paper ball, dropped it, and used Tracker to calculate its position, and then of course, did the coding in WebPython to get more expected and controlled values. So looking at these three graphs, we have on the far left, we have the expected values of a ball dropped for 1 second, or for 0.583 seconds actually. And in the middle, we have our paper ball being dropped, in which the paper ball is the system and the forces of drag and gravity are the surroundings. And then on the far right, we have the expected values of an item dropping, but accounting for drag. And looking at all three of these graphs, we can see that all of the graphs are relatively the same, but if you look at the values for the graphs, you'll notice the values for the graphs on the far left are almost double that of the middle and the right side. And that is because drag has such a profound effect on the ball that it slows it down, and at this point in time at least is almost going half as fast. And the initial conditions, if you look at the velocity graphs, are 0 for all of them. For the coding, this was just using basic velocity update and position update equations. And then for the drag version of the simulation, using the formula given for drag to account for that in the sum of the forces. And looking at the similarities and differences between these, like I said, you can see that there is all of the graphs look relatively the same, but there is a noticeable difference in the actual values if you look at the y-axis for all of these. And also looking at the velocity axis, you can't see it that much in the real values, but for the expected values, if you look at the one without drag compared to the one with drag, you'll notice that the velocity has a large change in it that is nonlinear, which shows a higher derivative being used than just acceleration. There's more forces going on than just acceleration being a constant value, which causes the velocity to change exponentially over time. So, looking at what does this mean? So what does it mean? Looking at these again, if we're looking at the velocity graph for the expected values of the ball with drag, we can see that it starts to bottom out. It goes towards a terminal velocity. In this case, that terminal velocity is around negative 1.8 meters per second. And this just happens because as the acceleration rises and the velocity rises, the effect of the drag starts to increase, which causes it to level out at negative 1.8 meters. For the what if we threw the object downwards initially? So now we have moved the original column that was on the right to the center and added a new column on the right. That is, if the ball was initially thrown downwards with a velocity of negative 10 meters per second, and we can see that the velocity actually slows down back to negative 1.8 meters per second. This is because, as I said, the graph will always go towards equilibrium because as velocity increases, the force of drag increases, causing it to slow down and eventually reach an equilibrium. And looking at air for these things, going back to our main graphs here, there is a lot of error in the calculated values just because using tracker is not the most accurate. Though the position graph looks to be relatively smooth, you can see the velocity graph is not a straight line and it's not even curved like the expected value with drag is. So that is everything for my lab. Hope you have a wonderful afternoon.